Hello and welcome to this short video on the central limit theorem. What I'm going to do over the next few minutes is show you how different distributions are mapped to the Gaussian, normal or bell curve distribution by the act of sampling. So what I'm going to do is start with a simple model which has no sampling, show you, set some baselines, and then go and show you the effect of sampling on the distributions. So in this model here, this is a Simulink model. I'm going to start off with a uniform random number generator which will generate numbers for me in the range 0 to 100. This block does nothing in this particular simulation. Then I pass the numbers through a histogram which has 101 buckets between 0 and 100. Each number that comes in is put into the appropriate histogram bucket. And what we get on the x-axis are the bins or the buckets 0 to 100, and on the y-axis it's the frequency of occurrence. So what we expect with a uniform random number distribution is a flat line. So for example, the number 50 is as equally likely to occur as the number 29. And what we expect is a frequency of about 0.01 for each number. So bear in mind we've got 101 buckets, so it'll actually be slightly less. Okay, what we've also got in this model is a mean calculation, which we expect to be 50. We also have a standard deviation, which we expect from the theory of uniform random numbers to be about 28.8. This box on the top right-hand corner is just counting out the number of samples. So for example, if we pass through 100 random numbers, this will actually say 100. So why don't I run this simulation and we'll have a look at what happens. As the number of samples builds up, what happens is this scope, this particular graph, starts to become more and more of a straight line. So we can see that we're now in the region of about 1,500 samples and it's getting a bit straighter. So why don't we take a pause here and come back to the simulation in a few minutes when we have some more numbers. So rejoining this simulation now sometime later when we've passed through some more samples, we can see again here that the uniform distribution is pretty much a straight line as we'd expect, and it's at about the 0.01 mark, which again we would expect from theory. And again, if we look at the mean, it's at 50, which we would expect, and the standard deviation about 28.8, which we would expect from theory. So far, so good. This is just a uniform random number distribution plotted out. But what happens if we take samples from this distribution and plot out the means of the sample? Okay, let's have a look at the next model that does this. So here's the next model. So it's the same as before on the top, but down here it's a bit different. What we do is we buffer up a group of samples. In this case we buffer up 10 samples and take the mean of those samples. And then we plot out a histogram as before and plot out a mean and a standard deviation. So what we're doing here is plotting the distribution of the means. I'll say that again. We're plotting the distribution of the means. This set of graphs at the top is the distribution of the underlying data. This plot here is the distribution of the underlying means of the samples. So we take samples, we're taking means of the sample, and we're plotting the means of the samples. Alright, so as we've seen here before, this distribution, the top one, right from the uniform random number generator, is uniform. It's a straight line. If we take samples, and then we take the mean of the samples, what shape should the distribution be? And the central limit theorem tells us that that should be a Gaussian curve. Okay, so whatever the underlying distribution is, when we take samples from that distribution and we plot out the means of the samples, we get a Gaussian. Alright, so let's go and run this simulation. What we expect then, if the central limit theorem holds true, is that this will be our uniform random number distribution as we saw earlier, and this will be our Gaussian. Well, why don't we run the model and take a look? Okay, we can see as before, it takes a little while for the samples, the distribution to settle down as we're passing data through the models, and I'll just move things so we can see, plotting about 1,000 samples through these models now. We can see on the right hand side, this is the uniform random number distribution, and it's kind of starting to settle down to a straight line, and on the left this is starting to look like a Gaussian. So why don't we come back to the simulation when a little bit more time has passed and have a look to see whether this actually does look more like a Gaussian. So now we're rejoining the simulation sometime later when some more samples have passed through, and we can see as before the uniform random number distribution is in fact random, but when we look at the mean of the samples taken from this distribution, we see this curve here, and it looks like a Gaussian, a normal distribution, or a bell curve distribution. And in fact I've done some fitting which I won't show you here, but that is in fact a Gaussian curve. And if we look at the data that's been calculated, and again we see the mean of the means is 50, no surprise there, but the standard deviation of the mean, is about 9.13. Now theory says that the standard deviation of the mean, this number here, is actually equal to the standard deviation of the underlying distribution, which is this number here, 28.9, divided by square root of the number of samples. So here we're taking 10 samples at a time, so it's square root 10. So it's 28.8 divided by square root 10 gives us, indeed, 9.1. So it looks as if in this fairly simple example, the central limit theorem holds, the predictions made by the theory are borne out by experiment, and it all looks good. But what if we take a more complicated distribution? So in this model, what I'm going to do is use a slightly different underlying distribution. Let's open here. So in this function, which did nothing before, what I'm doing is I'm taking the square root of the input uniform random numbers, multiplying it by 10. So I'm taking the uniform random numbers, square rooting them, and multiplying them by 10. And I happen to know that this will give me a triangular distribution. So why don't we run the simulation and have a look? And we see on the right hand side, this is the underlying distribution, and here is the mean of the samples. And what we can see here is that this is indeed looking like a triangular distribution as we pass some more points through, and this is starting to look like a Gaussian. So why don't we pause this simulation and come back when we've run some more samples through the model. So now we're returning to the model sometime later, and we can see that the triangular distribution is indeed triangular, but when we look at the mean of the samples taken from the triangular distribution, we see a Gaussian, and that is in fact a Gaussian. So we can see that for both the uniform random number distribution and the triangular distribution, when we take samples from those and we take the mean of the samples and we plot those out, we get a Gaussian. So let's have a look at the underlying results, and we can see that the mean value is about 66, which is kind of what we would expect, and again the same relationship holds between the standard deviation and the standard deviation of the mean. In other words, the standard deviation of the mean, in this case which is about 7.4, is equal to the standard deviation of the underlying distribution, which in this case is 23.5, divided by the square root of the number of samples, which is 10 in this case. So 7.3 equals 23.5 divided by square root 10, which is correct. Okay, so why don't we have a look at another much more challenging distribution? In this case, I've created my own distribution. It's like nothing found in nature. It's a kind of V-shaped distribution. So what happens then? Do we still get a Gaussian when we take the mean of the samples? Well, we're going to see. So this is a much more complicated distribution here. As you can see, it's very odd looking, but that's okay. This is a much harder test of the central limit theorem. So why don't I run the simulation now and we'll have a look at the results. So what we can start to see is a kind of V-shaped distribution being built up here. And then we can sort of see something that might or might not be a Gaussian here. So why don't we come back to this model when we passed more samples through, and we'll have a look at what the result is. So let's rejoin this simulation now that some more samples have been passed through the simulation. And we can see here that our distribution is odd looking, it's a kind of V, but that's okay. As I said, it's a weird kind of distribution, but it's a decent test of the central limit theorem. So what happens when we take this distribution on the right? We take samples from it, and then we take the mean of the samples. Well, once we do that, and we plot out the mean of the samples, again, we get, as on the left-hand side here on the red plot, we get a Gaussian. So again, this is what we would expect from theory, and it's what we see in practice. And let's again have a look at the numbers, and again we see the same relationship holds between the standard deviation of the underlying distribution and the standard deviation of the means here. So in this case, the standard deviation of the underlying distribution is 32.8, which divided by square root of n, which is the number of samples in each frame, or each buffer if we like, so it's 32 divided by square root 10, gives us 10.3, which is what we expect from theory. Okay, ladies and gentlemen, thank you very much for listening to this short presentation on the central limit theorem. If you've liked what you've heard, please leave me some feedback on YouTube, and what I will do is do some more videos. Ladies and gentlemen, thank you. Bye-bye.